Welcome to Genesis Unleashed, where we unleash the truth of Genesis.
And today I ask the question, did life really start off simple and become more complex over time?
A vital theme in the evolutionary story of life is that it goes from simple to complex, right? You start out over millions of years ago with a single-celled organism, and it goes on to get more and more complex and into a multicellular organism, and on from there, slowly over many generations.
Yeah.
That's the story of how it's supposed to work. And yet today we want to kind of have some fun and look at some fairly recent discoveries.
Right.
At the very, very small level, things that are happening inside our cells.
Right. And see if they're complicated or not. So you
Yes.
get the idea, right? Something that's simple, it has few parts, it's not complicated, not a lot of interrelated components, things like that. But just to set this up, here we'll just have a fictitious scenario here, and the viewers can decide whether you think what I'm describing, whether it's complex or not complex, etc. So let's say you've got a fella and he's working on his machine one day. Joe's working on some machine, and all of a sudden the machine breaks down. And so Joe's like, oh, what's going on? So he takes a look around, he does some kind of diagnostic here to figure, oh, look, and he finds the part that's broken.
Okay.
And so he removes the part, and it's whatever, part XJ92 or whatever. And he goes, oh, this is broken, so I can't continue doing work here. So he gets on his cell phone, and he flips it open, and he phones some manufacturing plant and says, I need this part, XJ92, could you ship one to me?
Okay.
So on the other end, they're saying, okay, no problem. They've got a pick list or something of the different parts that they manufacture, and they say, no problem, we can do that. What's your address? And so they record the address because they've got to get it to him. And then they discover, well, they don't have the blueprint to put that part together. So they're going to get on the horn and they're going to phone somebody else, a place where all these documents are stored, where the blueprint for that is located. And that gets shuttled over to their plant. And then now that they've got the blueprint, they can see how to assemble it. So they put this part together, and then they wrap it up in some kind of package. And of course, they need to shuttle it to where it needs to go. So they call a courier, and the courier comes along. He picks up the parcel. He looks at the address. He must compare that to some map, or he's got a GPS or something. And he travels to where it needs to be delivered, and presto, the parts are delivered on time. Now,
well, that sounds like a fairly complex scenario. All the technology involved, and cell phone, and likely GPS by the courier, and things like that. So, why are we talking about this?
Exactly.
Just hold on. We'll get there in a few minutes. But remember this fun little scenario.
Right.
That's obviously a very complex type of scenario.
Right.
So where are we going with this?
Well, we need to think about this. Of course, it's complex. Everybody recognizes that. Why do you recognize that? Because it's got all these integrated systems. It's got diagnostic systems. It's got database of parts. It's got shuttling of communication, shuttling of equipment, all that kind of stuff. So we know it's very complex. So what we want to do is actually take a look at something in cells of living things today, in the cells of what people would call fairly simple living things, and see if we can run some kind of an analogy here.
Right. We can look at just one component that links up with this story we're going to get here shortly. And this is in every living creature, in plants, in animals, in people, in things, and we could call them simple creatures. They say like worms and dandelions and clams and so on.
Right.
Everything has these. Everything that has a nucleus has these things. Cell, and it's called kinesin.
Right.
And so we'll.
Yeah. Let's take a look at a video here.
What's the kinesin?
Okay. Now, what you're watching here it's an incredibly small protein inside all eukaryote life forms. So they look like miniature robots. They've actually got 2 arms. They've got 2 legs. And one of the functions they have is, they've got many functions actually, but is to deliver packages from one place in the cell to another. So it's exactly like the scenario I was just discussing. Sometimes in cells, parts break down. And so some kind of signal gets sent to these manufacturing plants, these Golgi apparatus, and So this manufacturing plant, but they don't have the blueprint. The blueprint's, of course, in the DNA. So RNA knows to go and open up the DNA, separate it, get a copy of that blueprint of what's needed.
Wherever it is on the DNA.
Wherever it is, bring it back to the manufacturing plant. Now they've got the blueprint. They put the protein together. They wrap it in a bag. That thing you saw in the video, the thing that it was carrying.
It's carrying, yeah.
Because you saw it walking along this, what they call a microtubule, a roadway inside cells, a pathway, a road. And it's carrying this bag. And inside that bag are the proteins
that are supposed to be delivered to wherever the problem is, whatever part of the cell needs those proteins.
And so they get the proteins, they put it together, they wrap it in this bag, and then that gets imprinted with the address of where it needs to be in the cell. And then one of those little guys comes along, the kinesin, he comes walking along, and he picks up the bag, and then he's going to carry it to where it needs to be in the cell. He's the delivery guy. He's the longshoreman, he's the postman, whatever you want to call him, and he's going to deliver that. Now,
incredible. A number of questions come up. You're probably asking these questions already.
Yep.
How does the cell know which parts are needed? When part of the cell breaks down, there has to be some kind of a mechanism there where okay, well, I need this type of a part.
Right. It needs to recognize that there's something broken and which part is broken. So there's some kind of diagnostic program happening inside cells of creatures that evolutionists would call extremely simple. Way down on the evolutionary scale, so on. How does it know which ones are needed? Because if there's all these different parts in the cell, it's almost like having a catalog of parts.
So there would need to be something like a catalog.
Right, because it must go, okay, I need this part. Well, oh, you need this part. There must be some list here.
And then that wherever that catalog is, so that the cell knows, okay, I need it there. It also needs to be wherever that material is being manufactured.
Right.
So that they're communicating.
Exactly.
I need this part over here, and that wherever it's being manufactured is making the same part.
That's right. How does it communicate the part description? Because it's got to differentiate between all these different parts that it could be. So again, that's.
Yeah, okay, that's like Joe with the cell phone and the analogy there. So how does that communication happen?
Yep.
Some of these questions scientists are currently answering, working toward answers, and others, they're just questions that scientists are working on.
Right. I speak about this in one of my presentations I do at churches called Codes in Creation, and what one of our senior scientists in Australia, he says he calls the kinesin a gobstopper, which means people literally just They when you describe to them, that's happening right now inside your cells. They're kind of looking at you like, all right, what do you do with this, aliens or something?
The animation's pretty cool.
Yeah, and so people are just blown away. So, but the point is, it's not that whether even if scientists can figure out all these questions we're going to ask, that doesn't mean that it happened naturally somehow. It's just
right. It's just a communication of how complex these systems actually are. If we can answer the questions or not, it would be nice to have answers. And like a lot of the answers that are coming to some of these questions, how does it know this? How does it do that? How does it do this? And those questions speak of an even greater complexity.
Exactly. So how does it communicate the address? How can there be an address in the cell? I mean, for this delivery guy to deliver, if
there's got to be something. There's got to be something.
Some kind of map. It must have some kind of map or some kind of GPS, because if I gave somebody my address, and I say, I live in such and such a town in such and such a province or in such and such a country. If you didn't have a map to know where to start or know where you were in relation to that, you wouldn't be able to get there.
Right.
So that's amazing.
Another complexity is the roads that the kinesin walks on, the microtubules, need to be built.
Sometimes they're already there, but sometimes they're not.
Sometimes they're there. If they're not there, somehow the cell knows to construct the road that the kinesin needs to take to get to its destination, to deliver the package.
Yeah, and you can, if you want to just to grasp the complexities of what's going on inside cells, you can actually go to Harvard University. They've got a video called The Inner Life of the Cell that you can access on their website. And it's 5 minutes of computer animation detailing what's going on inside cells. And you'll actually see these microtubules being manufactured, and then you'll see the kinesin go along. It's just absolutely mind-blowing. It looks like some kind of video game or something.
Yeah.
But
And also DNAtranslation.info. That's one that we made.
Right.
And you can go to DNAtranslation.info and have a look at some of the processes of tearing apart DNA and reading it and folding the proteins and so on. Which is incredible. But back to kinesin.
How does the RNA know where to open the DNA? I mean, you've got this huge library of information in the DNA, but somehow it gets said, no, we need the plans for part XJ92. I'm just using that as an analogy, whatever. But it must be specific.
Somewhere in the DNA, it needs to know where to go to get the information to build that
Right. So if I've got an encyclopedia, and a 24-volume encyclopedia, that's like saying, well, I need book 19. I need, that particular book, but not just that book, but
19, chapter 5, page,
et cetera, et cetera.
Yeah.
And the RNA knows where to go. Unzip it. Okay, this is the information that we need. Well, then there must be some kind of comparison system there, right? How do you get the kinesin? How do you summon him? There must be some kind of signaling thing.
Like the cell phone type of thing.
Yeah.
How do you...
Walkie-talkie, whatever.
In your cells.
Yeah.
So.
How does it read the address, right? I mean, we have a system. I'm looking at this page. There's words there that communicate to me. How does the kinesin do that?
Is there some type of a GPS system? Is that the answer? And unbelievably complex.
You can go on and on and on with these questions, but we do know some of the answers to these things, or we do know some more about them.
Right.
As a matter of fact, I think it was about 15 or 20 years ago when people started to really understand about these little tiny molecular motors inside the living things, and the literature is still out there, but it's not that commonly known. But kinesin can actually go into sleep mode. There's actually a motor called ATP synthase that produces ATP. That's like the universal life currency of all living things. And kinesin, they take an 8 nanometer step as they're stepping along inside the living things. And
every time they get hit by ATP, then they take one step.
Right. And just for scale here, if you took a meter and you cut it up into 1 billion pieces, 1 billion, 8 nanometers would be 8 of those billionths of a meter. So we're talking micro-technology here. These things go into sleep mode. So if they're not doing work, if they're not delivering something, they kind of fold in half and just go to sleep. And then when they're needed, they come back to, well, not life, but they're not living. They're just like little biological machines. And they start, because you don't want to waste energy when you're not working. It's amazingly complex. If they're going along and the microtubule they're on is busy, maybe there's other kinesin in the way, or there's just some kind of blockage, they actually know to reroute, just like your GPS, right? Oh, can't go this way. Boom, route. Take a different route, and they'll go around. Recomputing. That's right. Kinesin, most of them start from the inner, the core of the cell, and they move to the extremes. That's the way most of them work. Some of them work on the way back, but most of them go one way. So when they get to the other end, they're either transported back to the cell, or sometimes scientists think now that they're broken down into component parts and recycled. So the cell's knowing to do that as well.
So they don't walk back themselves. What do they thumb a lift?
Yeah, there's another motor protein that supposedly brings them back. Sometimes it's like a relay race. Sometimes the kinesin will be going along, he'll have his package, he'll hand it off to another one, and they'll take it from there.
Okay, so then the other kinesin needs to know the address that's on the package.
Right, and they need to know, okay, hey, you need to deliver this here. I'm doing something else, or again, multi levels of communication that needs to be going on inside cells for that to happen. And sometimes they actually team up to carry a single load. So you'll have, if it's really heavy, you'll have many of them. Okay, let's all pitch in here and a coordinated effort.
So again, we find these things in pretty well all forms of life.
Any multicellular life, kinesin are actually involved in getting cells to split apart, and they do a massive amount of function. We're just talking about one aspect of them here.
That's amazing.
Yeah, so unbelievable. What's really amazing, I was doing some research, of course, getting ready for the show here, and found some new information about the speed of these things. It's mind-blowing, unbelievable. So here's a direct quote, we'll put it up. It's, the title of the article was Kinesin, What Gives? That doesn't sound like a very scientific, but it was just, I think, expressing the fact that it was so mind-blowing. They were like, what gives?
Right.
And from Princeton. And the quote here says the kinesin motor is impressively fast, capable of 800 nanometer steps. 800 nanometer steps, so 100 steps per second. And it's quite powerful, continuing to move against loads up to 6. I don't know what that actually stands for there, but that's incredible. 100 steps per second. Okay, so that would be like me moving 600 feet per second. If you provided the scale, if you figure out how big a kinesin is, and you figure out how 8 nanometer steps, and then you figured that out, that would be like...
Kind of extrapolated up to human size.
Yeah, and I know that's kind of unfair in a sense to do that.
What's that in like miles per hour or something? You've worked that out, right?
No, I don't think I've worked out miles per hour, but 600 feet per second, I mean, you're the Flash, right? You're like, boom,
yeah,
you're there.
Yeah.
And so I will read the next quote here to put it in perspective. Scaled up to our own dimensions, a motor with corresponding properties would travel at similar speeds and produce as much horsepower per unit weight as the jet engines of the thrust supersonic car which recently broke the sound barrier. And there's a picture of the thrust supersonic car. So that's 763 miles per hour or something like that.
So this thing's walking that fast, right?
Right. That's the thing that's so incredible when I thought about it. It's like, this isn't just some electrical signal that's, can travel very quickly because this is an actual stepping motion. So it's actually like moving its legs. So it's like, I mean, when you see the animation there, he looks like he's just juggling. This is like,
that should be sped up, yeah.
It'd be like, here, we'll show it for you guys. Hey, you want to see it again? It would be that fast, right? It's just amazing. So here's a couple more quotes to just put things in perspective from some scientists that are studying these things. From an evolutionist, our results show that that a molecular motor must take on a large number of functions over and above simple transport if it wants to operate successfully in a cell. It must be possible to switch the motor on and off. It must be able to accept a load needed at a specific location and hand it over at the destination. It is impressive how nature manages to combine all of these functions in one molecule. In this respect, it is still far superior to all the efforts of modern nanotechnology and serves as a great example to all of us. Well, folks, it doesn't really take much when you really consider it. If these things that are in the simplest of life forms, or some of the simplest life forms, supposedly way down on the evolutionary scale, if it is beyond our technology today to produce this type of thing, then obviously these things are not simple. And obviously when we look at technology like this today, we attribute it to an intelligent cause.
To design, of
course. To design, to a mind.
Highly, highly intelligent design.
The Bible states clearly that no one will be able to deny the fact that there's a God because of what God created. Romans 1:20 says you can know there's a God because of what He created. Even if you don't know who God is, you should be able to look at things like this and just say, that is incredible.
It's amazing how hard people fight against the obvious.
That's true.
There's so much design all around us, and the comments that we get at creation.com, for example, the comments that come in via email and things like that, it's just the evidence for design, for an intelligent designer, for the God of the Bible, let's just be plain about it, is everywhere.
Right.
It's just amazing. And to try to push that away or censor that out, it's sad in a way. It really is sad.
That's right. So some great evidence. As some people say, oh, it's not scientific to believe in God, or religious people, you're not rational because of science. Science is a great help to belief and faith in the God of the Bible, because when we see things like this, we can truly understand that we're fearfully and wonderfully made.